What's up, everyone? In this lesson, we're going to be talking about some dilation. A dilation is a scaled image. So, it's also like you can think about the stretch or a shrink of a figure. So, when we think of dilating, we might think of pupils, right? And if you see this GIF over here, the pupil is shrinking and then it is enlarging. So, that's the idea of a dilation. We are shrinking and enlarging images. Now, a dilation, this is a more geometric example of something you might see. It's a scaled image. And again, we've dealt with scale factor and scaled images back when we did triangle similarity. But remember, we might have heard this term scale factor before. So for a dilation, we need a scale factor, which is usually denoted by the letter K. And we need a center of dilation. So similar to when we did rotations, we had a center of rotation, right? And that center of rotation didn't change. It's the same idea for our center of dilation. Our center of dilation is not going to be affected by the rule. Now, we always like to relate these transformations back to the fact, hey, are they rigid motions or not? Well, since a dilation is changing the size of a figure, it cannot be a rigid motion. Remember, rigid motions preserve distance, or they preserve side lengths, or they preserve size, right? And a dilation is exactly the opposite of that. A dilation is you are purposely shrinking or enlarging an image, so a dilation is not a rigid motion. Now, we are changing the size of a figure, but if you remember when we had scale factors and we dealt with similar triangles, what you still want to keep in mind here is although we are changing the size of the figure, the angles are not going to change. So if you have two figures and they don't just have to be triangles, but if you multiply all of the sides of this triangle here, of ABC, by your scale factor of K, your angles are going to be untouched. So no matter how much you're enlarging your figure or how much you're shrinking your figure, your corresponding angles are always going to be congruent. And this goes back to our unit on similarity, but again, you can just remember that fact. No matter how big or how small you are making your figure, if you have a scale factor involved in there, your corresponding angles are going to be the same. Now, talking about scale factor, so here's a formula that you guys can use. So your scale factor, you take a new length on your image and you divide it by an old length on your pre-image. Now, talking about scale factor in general, if our scale factor is 1, our image is unchanged. So image unchanged. So what that's like is having a triangle here with side lengths of, let's do 3, 4, and 5. A dilation with a scale factor of 1, we'd have to multiply all 3 of these sides by 1, and again, we would result in another triangle with side lengths of 3, 4, and 5. So if that's the case, if our scale factor is 1, then our image and our pre-image are going to be exactly the same. If our scale factor is greater than 1, our image is getting enlarged. So again, think about if you have the same side or the same triangle with lengths of 3, 4, and 5. If your scale factor is something like 2, 3, 4, or 5, these side lengths are only going to get bigger, right? So another notation that you might see is whatever your scale factor is, let's say our scale factor is K, you can multiply that by all 3 of your sides. So you might see K times 3, K times 4, and K times 5, right? And no matter what your scale factor is, as long as it's greater than 1, your image is going to be enlarged. Now, if your scale factor is less than 1, your image is going to be shrinking or getting smaller. So that's the idea. Again, if you take side lengths of, let's do a different example. Let's do like 2, 4, and 6. But then let's say our scale factor is something like 1/2. If K equaled 1/2, then we'd be multiplying all 3 of these sides by 1/2, or halving each of those sides, and it would give us a triangle of 1, 2, and 3, right? So here you can clearly see that our image is shrinking. So it's a good idea to conceptually think about whether your image should be unchanged, enlarged, or shrunk, because sometimes that might help you provide validity to your answer. Now, this is dilation notation, so we always have this capital D, and then we have this subscript K, and again, remember that subscript K is the scale factor, and it can be 1, less than 1, or greater than 1. So we're going to do some examples. So the first example, we are going to deal with dilations with a compass. So in this first example here, we're going to be dilating this triangle with a scale factor of 2, centered at point A. So remember, your center of dilation is not going to change. So A is going to be equal. I already know that A is going to be A prime. Like that point, since it's my center of dilation, is not going to change. And since we have a scale factor of 2, we need to double the length of each side. In other words, we like to think about dilation as like manipulating our distance from the center. So in this case, our center is A. So if our scale factor is 2, I want to double the distance from B to my center of dilation. And I want to double the distance from C to my center of dilation. That's kind of how it's worded, right? So if you guys remember, when we want to double the length of a segment, we have to draw a line so that we have a reference. We put our needle on our center of dilation here, and we're going to make an arc on B to show that distance, and then we again are going to make that arc. We're going to move our needle over, and we know that B prime is going to be at this intersection right here. And again, what we know from this is I know that the distance from B prime to A, I know that that's double the distance if I measured from A to just B. Okay, so I know this is double. Now, again, we have to do this for C as well. I'm hoping I have enough room here. But what we want to do is we are going to draw our segment so that we have a reference. And then our needle is going to go on A. And we want to measure the length to C. And then we are going to bring our compass up. And I have just about enough room. I don't know that it's going to show, but it's actually at the top of this page up here. But C prime, and you guys should mark C prime at that intersection, C prime is all the way up there. And again, what we know is that the distance from C prime to A is double the distance from C to A, right? Double the distance to our center of dilation. Now, what we can do is take our straight edge here, which is just a segment tool, and we can connect B prime and C prime, and that would be the dilated triangle. Now, in this second example, what we are going to be doing is we have a scale factor of 1/2, but now the difference is our center of dilation is off of the figure. So again, we are dealing with the concept of either enlarging or shrinking this distance from our center of dilation. So our scale factor here, our K value, is 1/2. Now, if you remember, when we have to halve something, the mathematical or geometric fancy word is we need to bisect it. Now, this is a construction that we know and love very well. But before we do that, we are just going to draw some segments with our straight edge from our center of dilation. Let's do B first. So we'll do from our center of dilation through point B. Now, the reason we are doing this is, again, so that we have a reference, because what we are going to do is we are going to bisect the segment from O to B. Now, in other words, we are halving the distance from O to B. If our scale factor is 1/2, we need to bisect that segment OB. Now, how we do that, and if you guys remember this, right, we go more than halfway of the distance, and then I'm not going to make full arcs. You guys can make full half circles if you want to. But it's going to get very messy here. So I'm just going to draw arcs at the top and the bottom. And again, I'll put my needle on B, and I go at the top and at the bottom. And you should have intersecting arcs here. And we take our straight edge and we connect those, right? So I know that B prime is this point right here. Now, again, what I can guarantee is that the distance from B prime to our center here is definitely half the distance from B to our center, right? Now, you can probably imagine we need to do this 2 other times. So let's do this for A, and I'll use a different color. So we create a segment. You know what you can probably even do? You probably don't even have to go all the way through. But I don't know, sometimes you might see it going all the way through. So I'm going to draw it all the way through. And again, the idea here is that we need to bisect the segment connecting O and A. So again, this is the distance of O and A, and we go more than half of that distance, and we need to connect or make our arcs intersect above and below the line. Then I'm going to move my needle to A, being very precise here. Notice that I have my compass locked. You can't lock your compass, but you can make sure that it doesn't move. Okay, and then we take our straight edge and we connect here. And then we know that A prime is this intersection point. Now again, what I can guarantee here is that the distance from A prime to O is going to be half the distance from A to O. That's, again, the idea here. Now, we'll do this last one in green, going a little bit quicker. And I won't go all the way through, just so you guys can kind of get an idea of what it would look like if I didn't extend this segment all the way out. But there's segment OC. And again, we want to bisect that segment to get half of the distance. So again, we go more than halfway. And now our picture's getting a little bit messy. But as long as we go slow and follow our steps, we should be good. So we make arcs at the top and the bottom. And then we move our needle around over there. And if our arcs didn't intersect, we would just have to go back and extend them just a little bit. And we do actually see that problem here. So here, my arcs are not intersecting, right? So in this case, I got to go back to O and extend this arc just a little bit, just so that they do intersect. Now we're connecting our intersection marks, and we know that C prime is right here. And again, what we can guarantee is that the distance from C prime to O is half the distance from C to O. Right? And now last but not least, let's take, I'll just do it, I guess do it in purple. We got a lot of different colors going on here, but that's okay. We're doing it purple, and we're going to connect A prime, B prime, and C prime. So A prime and B prime are connected here, and then B prime and C prime are here, right? So if I shaded this in, our triangle A prime, B prime, C prime would be right here. And again, now we can guarantee kind of two things, right? We can guarantee that triangle A prime, B prime, C prime is half the size of triangle ABC, but then we can also guarantee that the distances of A prime to O, of C prime to O, and B prime to O are all half of the distance from A to O, B to O, and C to O. Okay, so again, these pictures can get pretty messy, but just make sure you're going slow and following your work as you move along so that you don't need to retrace any of your steps.